invitation. Actually, I changed the order of the questions a bit to make it a bit easier to talk about this. So we will start with the how in machine-based decision-making. So traditionally, classical approaches to support decision-making in the clinics are knowledge-based systems. We've heard already about guidelines, which can be implemented also in computer programs. That's required for assigning patients to medical imaging in the US already. Then there are the physiological and biophysical models, which can be used to simulate the effects of drugs, physical stress, interventions, and in that way help to make the right decision on how to treat a patient. So nowadays we are facing the so-called diagnostic dilemma. Therapies should be more individualized. There is the medical evolution, so there are new methods for getting new biomarkers, and data increases, and complexity in decision-making increases. So it's very difficult to decide how to implement this into the classical tools for decision-making. So that's why people are turning towards data-driven modeling to support decision-making. And the idea is very simple. So you have example data, and in the easiest case, you really only have example data and need a computer to help you make sense of it. And in some cases, you have example data that involves, on the one hand, the data you want to put in, and on the other hand, the results you want to get out. And then the new approaches for machine learning just try to make sense of what gets in and what should come out. So there are several fields which are closely related here, and they all focus on working with huge amounts of data and interpret the data towards supporting decision-making. For example, in data analytics, people focus on how to store data, how to clean data, and how to make data available so that it's possible to see information in the data sets. Then we have the computational statistics, you all know, which is already very successfully used in computer-aided detection approaches. And then we have the machine learning. And machine learning is defined such that the computer improves in some given tasks based on the experience, so based on the information he gets to be trained. And then we have the unsupervised learning, where we really simply put in data and want the computer to help us make sense of it, so find structures in or hidden patterns in data. We have the supervised learning, where we have some sample information. For example, in the field of medical imaging, we have image data and we have samples on how the result of a segmentation should look like, and then the computer should learn the rules to make the connections between input and output itself. And then we have the reinforcement learning. This is something where the computer continually tries to adapt to input and output requirements. So to go even more into detail, there are many, many approaches for supporting supervised or unsupervised learning. And you see that in all these fields, there are the neural networks. So the neural network seems to be an all-rounder which can apply it for almost every problem. What does it mean? So the neural network concept is a programming paradigm that is inspired by biology. And it's based on the concept of a so-called neuron. A so-called neuron is a basic structure which gets some input information. That would be the data you would put in for the decision making. Then it calculates the input function based on some weights. And then there's the activation function. The activation function takes the result from the last calculation, then the information from the input function, and then some threshold, and based on this, the output is calculated. So when we talk about learning here, it means for a neural network that we try to derive the parameters of the neuron. The parameters a neuron uses to calculate the output. These are the weights, and this is the threshold. And if you look at supervised learning, we know what output we would expect for certain inputs, and we calculate an optimization based on the difference between our expected output and the current output of a network. And by this process, we train our network. In the case of the unsupervised learning, where we do not know correctly what we want to get out, we try to minimize the standard deviation within the classes the computer detects. So when talking about networks, we put together several layers of these neurons. And by this, we can have very complex calculations and solve almost every problem. So for example, this is the network architecture for a classification problem recently published. Then there are networks for time series modeling. That would be some reinforcement learning approach here. And then we have the famous UNets, which are at the moment very popular for image processing. And I will talk a bit about image processing because that's my subspecialty. And there is the concept of the autoencoder. So if we want to feed images which can be can look very different and have very complex information in such a decision-making network, we have to provide a proper representation of the data. And the idea of the autoencoder is that we take an image and let the network make some compression suggestions, and then try to reestablish the original information to see if the information that characterizes the image is captured by the compression. And in this case, we see our output image looks different. If we compare it with our input image, that's a calculation of the so-called loss function, then we still have a relatively high value, and that would mean we need some more training. And I'm very sorry that this movie doesn't work here, because that would show you how these compressions and re-establishing of the original information would improve with training in such a network. So let's look at some real problems that should be solved by a network, like, for example, segmentation. And I'm sorry that it's livers here, but that's what we've been working on in the past. And here is some example that would also be a movie, but I can explain it like this, where you see this curve. This curve on the left shows you on how well unseen data is segmented by a neural network after being trained with a certain amount of examples. And you see, in general, with more data in the training data set, the segmentation performance improves, but there are some points where the segmentation performance became worse with additional data. And that's one of the major problems when working with these approaches. You can confuse such a method very much with putting in data that's not representative for the problem you have. And of course, looking at this, we can segment livers with very different shapes now. You need a very, very large training data set to achieve this. So coming to the what question. So what can machine learning actually do for you? I have gathered some examples, such as, for example, applications in the field of image acquisition. So this is a recent publication where neural networks were trained based on fetal ultrasound data and now are able to tell you in real time what you see on your current imaging plane. Then there are lots of approaches currently developed in the field of automatic image processing and quantification. And this is an example of an approach which enables you to calculate the right and left ventricular volumes of a cardiac MRI dataset totally automatically. Convolutional neural networks have also been successfully applied for individual risk prediction, and this is a recent publication where people trained based on a huge population of, I think, more than 200,000 patient datasets, and achieved a slightly better risk prediction for cardiovascular disease than the guidelines would do based on different machine learning approaches, the best of which was the neural network here. Then we also have good results in the field of sensor interpretation. And here the neural network monitors the ECG signal of a patient and outperforms the cardiologists in detecting and classifying arrhythmic events. So one approach where the unsupervised learning could help you is in the field of phenotyping. So here's an example where machine learning has been applied to data sets from heart failure patients and was able to subgroup these patients. So let's go to the when question, and does this work? I'm sorry. So, okay, you see the quote here. This is would be from a panel discussion involving luminaries in the field of deep learning, such as Geoff Hinton. And what Geoff Hinton was telling at this panel discussion was that he assumes it will be about 5 years and then we won't need radiologists anymore because the computers will outperform the radiologists in the interpretation of image data. And then, okay, because people were really upset, he said perhaps it's 10 years, but he was totally sure about this. Asking some people who are in the field of cardiology, there is this group from Brickens and Women's and MGH who every year publish the disruptive dozen on some medical field, and this year it was cardiology. And they select 12 technologies from which they expect that they will have a high clinical impact, that they have a good potential for making it to commercialization, and where they expect that they will be ready for market within the next 10 years. And not surprisingly, number 2 is big data and deep learning for clinical decision support. So if you ask the experts, we are very close to having these methods available for clinical routine. But of course, there are several challenges on the way there, such as, for example, the regulatory constraints. And time ago, people said these methods will never make it into clinical products because they will never get the approval, because it's like a black box. You saw this heap where you put data in, get something out, and you do not really know what the computer does in between. But the statements of the FDA are such that they are really open to these approaches, and it's not that they expect from every modeling approach that you can explain mechanistically each step, but there are other ways to prove that an approach is suited for clinical application. And just this year, they gave the FDA approval to a medical image processing product that does machine learning, is based on machine learning in the cloud by the company Arteris. So the biggest problem regarding the regulatory constraints may be the data security issues which prevent hospitals from providing their data to such approaches. And that's related to the approach to the problem we developers face here. So in order to achieve good results based on machine learning, we need the proper input data. And in the current situations where the rights on the data, so does the patient have a say in whether his data is used for training products in with machine learning, or whether the hospitals are allowed to put their data into such approaches, it's very difficult to develop a strategy for building such methods. And of course, if we want to work with the huge amount of data we can put into such methods, we have to integrate our solutions within the existing IT infrastructure, which is also complicated. So there are some approach towards this, trying to deal with the regulatory constraints we have, for example, in Germany, where the data must not leave the hospital. And that could be that clinics are provided with deep learning training servers, which are attached to, via a node that collects the data and provides it after some pre-processing to the training server, then train the server on the available data, and exports the trained deep learning network after monitoring the performance, of course, provided to the so-called classification server. So that would mean that the classification server could be everywhere, work with the experience gathered from some hospital data, and apply this to data from other hospitals, for example. And it might also work in such a way that pre-trained networks could be exchanged between institutions to get more experience with more data that's available everywhere. So in the end, you see, it all depends on what we feed in and how we deal with the technology we have. And in the end, real stupidity beats artificial intelligence all the time. Thank you very much.